We will look at the large signal characteristics of the CMOS inverter. A CMOS inverter is realized by combining a PMOS common source amplifier with an NMOS common source amplifier. And in particular, the same bias voltage and the same input is given to both transistors. This is Vi, this is Vo. Okay. Now, as before, to plot Vo versus Vi, we choose the graphical method where we plot the characteristics of both MP and Mn on some axis. For this, we choose this I, that is the current through both transistors, and the voltage V0 as the variables. Now, for the PMOS, the source gate voltage is VDD minus Vi, and the source drain voltage is VDD minus Vo. And for the NMOS, the gate source voltage is the input voltage Vi, and the drain source voltage is Vo. Now, we plot the characteristics on I versus Vo axis. As before, I versus Vo for the NMOS transistor, it's the same as the ID versus VDS characteristics. Now, the input voltage Vi determines the gate source voltage. So, we have to draw ID versus VDS for different values of VGS, gate source voltage, depending on Vi. Similarly, for the PMOS transistor, the I versus Vo characteristic is related to ID versus VSD characteristic, because VSD is VDD minus V0. So, I versus Vo will be simply a reflected version of I versus VSD characteristics. And again, for this also, VSG, the source gate voltage, is dependent on Vi. So, for every value of Vi, we will have to choose a different value of source gate voltage. Okay. Now, first of all, let's start from a small value of Vi. Let's start from Vi equal to 0. If Vi equals 0, this transistor Mn is turned off. In fact, for Vi between 0 and Vt, N, the threshold voltage of the NMOS transistor, this transistor is turned off. So, that means the current I is 0. For values of Vi between 0 and the threshold voltage of the NMOS transistor, this transistor is turned off. So, the current is 0. Whereas MP is turned on because we assume that it has a large enough VSG. So, the output voltage will be at VDD. We can also see this graphically. I versus V0 characteristics or ID versus VDS characteristics of the NMOS will be just the 0 current line. This is for Vi between 0 and Vtn. Now, as Vi increases from 0 to Vtn, the characteristics of the PMOS transistor changes. Okay, when Vi equals 0, the characteristic may be something like this. Okay, I have shown the reflected characteristics from the previous examples. This must be familiar. So, this is the PMOS characteristic for Vi equal to 0, which means the source gate voltage equals the supply voltage. This is the maximum possible value. As Vi increases, the point at which it reaches saturation moves, and also the current itself decreases. But because the NMOS transistor is off, it always intersects here. So, the output voltage will simply be equal to VDD. For inputs between 0 and Vtn, the output will be exactly equal to VDD. Now let's start from the other side. Let me start with Vi being VDD. Then the source gate voltage of the PMOS transistor is 0, so the transistor is off. Okay, and we expect that the output voltage will be equal to ground. Okay, because for the drain source voltage of NMOS transistor to be 0, when it is on, it has to have 0 drain source voltage. Okay, now the NMOS transistor has a gate source voltage equal to VDD, so its characteristic will be like that. So let me assume that this is the NMOS characteristic for VGS equals VDD. Now as Vi reduces from VDD, this characteristic will change. But as long as the input voltage is between VDD and VDD minus the threshold voltage of the PMOS transistor, the PMOS transistor's characteristic is simply a zero current, a zero line. So the point of intersection is here, so the output voltage will be 0. Okay. It will be like this. Okay, so in this part the PMOS is off, and in this part the NMOS is off. Now let's look at this region when the input is slightly more than VTN. As the input increases beyond the threshold voltage, the NMOS characteristic will be like this, with a small saturation current. By saturation current, I refer to this flat part of the current, that is the saturation current. Okay, and the PMOS characteristic will be something like this. So it's clear that at this point the PMOS transistor is in triode region, whereas the NMOS transistor is in saturation region. Okay, it will be like this. So the output voltage falls as it goes from here to there and so on. Okay, finally we reach a point where both transistors are in saturation region, and as with the previous cases, when this happens the gain is very large. Okay, small signal wise, this means that in saturation region GDS values are very small for both the NMOS and PMOS transistors. So GMP plus GMN divided by GDSP plus GDSN will be large. Alternatively, graphically you can see that if two nearly flat lines intersect, small movement in either of the lines will change the point of intersection by a large distance. Okay, so the slope becomes larger. Like I said, here the PMOS is in triode and the NMOS transistor is in saturation, and here both are in saturation region, and we'll eventually reach a point where the PMOS characteristic will be like this and intersects the NMOS characteristics here. So NMOS will be in triode region and PMOS will be in saturation. Okay, So these are the large signal characteristics of the CMOS inverter. It looks similar to the previous two cases where the input was applied only to either the NMOS transistor or the PMOS transistor. But the crucial difference here is that the output does go all the way to VDD or all the way to 0 at the two ends. Whereas in the other two cases, either it was going all the way to VDD but not to 0, or it was going down all the way to 0 but not all the way up to VDD. Okay, this offers some advantages, and this is actually a very popular building block of digital circuits. Okay.